Welcome to another podcast. This episode we're going to be taking a look at some of the terminology, notation, and ideas behind solving a system. What do you end up with? What does it look like? How can you recreate it? We're even going to bring a little bit of Maple in here to discuss how to create the graphs that I have on the screen. This is the exact same system that we looked at in the previous video, so if you haven't watched the video on solving a system by elimination, this was the system that we looked at. If you recall from that video, the solutions that we ended up with were of the form x of t is c1 e to the 5t plus c2 e to the negative 2t, and y of t was equal to c1 e to the 5t and minus 3 C2, oh, it was 1/2 C1 e to the 5t and minus 3 C2 e to the minus 2t. So that was our solution from last time. And what I want to do this time is talk about what are the ramifications of finding the solution of a system. So I want to start with the idea of what the solution looks like. So the solution itself is of the form x of t, y of t. It's a coordinate pair that depends on time. Well, we know these as parametric curves. So this is a parametric curve, and you can see that this is the graph of the solution in what's known as the phase plane. So this is called the phase portrait or phase plane of the solution. It is a graph of the dependent variables along each of the axes. So this is x changing over time, this is y changing over time, and you can see that the points in the plane are plotted x, y as functions of time. We call those parametric curves. Or sometimes you'll hear it talked about as a trajectory. So the idea is a solution to a system is a parametric curve. And the important distinction here is that this is not necessarily a function. If you think about everything we've dealt with up to this point, we've only been dealing really with functions. Now we've had some discontinuous functions, but we've only ever been able to come up with solutions that were functions, and that is severely limiting because there's lots of models out there that are not functions. There's lots of models that are modeled with much more complex relationships between their inputs and outputs than being a straight one-for-one relationship like a function would be. That makes things more complicated. It also makes things much more interesting now. We have access to a much larger variety of possible solution behaviors by recasting problems as systems and treating the x and y variables independent of each other as the two dependent variables of the system. And so this is called the phase plane portrait. And over here you can see I have a graph of t versus x. And here below I have a graph of t versus y. So looking back over here, all of these graphs, by the way, are for the IVP, where you can see here the initial point is right here on all of them. The initial point is x is 1. And y is 0. So the way that we treat that in an IVP is we say x of 0 is 1, y of 0 is 0. These are our initial conditions. And if we write it in matrix form, the initial conditions are actually a vector. It's the initial vector. So the matrix form of this system would be xy prime equals, coefficient matrix here is 4, 2, 3, negative 1. And then the initial vector is x of 0 and y of 0 are equal to 1, 0. That's the initial vector. And so this is an IVP. And so you can see here on each of these, when time is 0, x is 1. So this is 0, 1. And when y is 0, it's 0, so this is 0, 0. So you can see the initial conditions show up in each of the graphs. Now, I want to go ahead and bring in Maple. and talk about how I came up with these graphs and how in general we're going to solve systems in this unit. So in Maple, we're going to load the DE Tools package, and the difference between systems and linear equations is you have sort of this dependency on two equations. So you can see here how I've taken each of the two differential equations and I've bracketed them. That tells Maple that this is a system. So I want to solve the system for, and remember down here I wrote the solution is this parametric curve, this coordinate, and so you're telling Maple that the solution is grouped x and y as the component solutions. And so if I do a desolve for that real quick, we get our solution, and if we compare it, we're going to see some differences, and I'll talk about those differences here in a second in a couple of remarks. But this is our solution. So this is how the x coordinate varies, and this is how the y coordinate of our parametric curve that's the solution varies as well. Now, if I wanted to graph these, the easiest way to do that is by revisiting the DE-plot command. And in particular, we do it just like we do the desolve command above. We would have the system entered, bracketed, the solution variable x of t, y of t combined, and then you have to enter ranges for all three variables. You have to enter ranges for every independent variable as well as every dependent variable. And then, like I said before, this is the initial condition, so if I actually wanted to see anything show up in a plot, I'd have to do this. And hopefully you remember the scene command from earlier in the semester, but just in case you don't, basically what it says is once you get ready to plot the solution, I want to see t as the horizontal axis, and I want to see x as the vertical axis. So you can see here that t comma x gives t and x of t. By the way, these are called the component plots. So I'll write that on the other screen here in a second, but this is the component plot of t versus x. And then to see t versus y, all I do is change the scene to be t and y of t. And so there is the graph of the solution for the y component. And then finally, if I wanted to see the phase portrait, you're graphing both x and y together. So x would be the horizontal axis, y would be the vertical axis. And if I plot it like this, it's going to give me arrows that define the slope field. So you can see all of the different behaviors in here. And if I didn't want the arrows, I would just say arrows equals none. So we've seen that command before earlier in the semester. But this would then be the phase plot that you can see right here. So this is the phase plot or phase portrait. So all three of those combined are really nice. And then the third one is if I wanted to graph t, x, and y all on the same graph, then that would be a three-dimensional graph. So I need to use the command deplot3d. And in order to use that command, there's no arrows on that plot. And the scene there would be t, x, and y, all three of them plotted together. And so if you plot that, then you get this nice little three-dimensional graph where you can look at all of the dependency together, including time along this axis. You can see x along this axis and y along the vertical axis. For some problems, it's very helpful to look at this plot. This is called a composite plot. And so, just reminding you of some terminology here. These plots that we ended up with, both here and here, these are called the component plot. Component plots because you're plotting x and y, and those are usually called the component solutions. And then if you plot t versus x versus y, so all three of them, this is called the composite plot. And that's done with the deplot3d that we just showed. So I have a couple of remarks that I want to make here about what's going on. The first is I want to write my solution, the solution that I have here, in a different form. And so I want to treat the solution as if it were a vector. So this would be the vector xy equals, and I want to break out the c1s in the exponentials and then just have a vector of the constants that show up. And what I mean by that is you have c1, and then if you look at e to the 5t, it's 1 divided by, or not 1 divided by, but 1 for the top component and 1/2 for the bottom component times e to the 5t. And then similarly for the second one, the scalars are 1 and -3, both of them times c2 and then e to the -2t. Now that actually, we get a lot of mileage out of this, and the reason that I wanted to bring it up is if you go back and look at our solution given to us by Maple, so if we go back to the dsolve command, it doesn't look exactly the same. In fact, let's go ahead and write it down. The solution from Maple is x of y equals C1, and their component for e to the 5t was 2 and 1, and their component for C2 was 1 and negative 1/3. And so I want you to take a look right quick and compare vector for vector in each of these two formats, and notice that the ratios are the same. So the ratios of those match. In other words, the only difference between Maple and ours is a constant multiple. In other words, if you take the solution we found by elimination and multiply that vector by 2, you get the one that Maple had. Similarly, for the other vector, if you multiply it by, let's see, it looks like, oh, actually I got that mixed up. It's negative 1/3 for the top component. So it's negative 1/3 here and 1 here. So you can see that the ratio there is by multiplying by a negative 1/3. Here it was by multiplying by 2. And so they are constant multiples of each other. What this is meant to show you is that only the ratios of these vectors matter. And that's going to be an important thing for us to understand going forward. It turns out that there's some really deep mathematics at play here. So I actually want to say a little bit more, and I'm going to need to create some room to do that. So if you'll bear with me here, let me just go ahead and get rid of these graphs over to the side. Too much. I didn't want to get rid of everything. So if I get rid of these graphs over to the side here, what I want to look at now, so this is sort of my next remark, is that there's actually a really nice format going on here. So let me pull out each of these pieces. I want to pull out this piece here and this piece here. So I'm going to call this piece x1. So this is the vector x1, and this is the vector x2. And they are legitimately vectors. If you take this vector times that, e to the 5t, that's a vector for the solution. So these things right here, so x1 equals e to the 5t and 1/2 e to the 5t, and x2 equals e to the negative 2t and negative 3 e to the negative 2t. These are called the fundamental set of solutions. And what's interesting about that is if I want the actual solution, x of t, then the idea is that what we just discovered is x of t is nothing more than c1. So in other words, if x of t, so let me write it this way first. X of t is the solution vector containing both x and y. I can write x of t in terms of this fundamental set, and it would just be c1 x1 plus c2 x2. And so that is very reminiscent of things we did earlier in the semester, that this is a fundamental set of solutions. You need two sets because it's a second order, it's a first order 2x2 system. So since it's a 2x2 system that we were working with here, we actually needed two. We need two, and the word we used before was two linearly independent solutions. And it turns out the way that we can talk about linearly independent is the same way we talked about it earlier in the semester, and that is the Wronskian. So what is the Wronskian of these linearly independent solutions? Well, it's simply this really obvious determinant here. It's this e to the 5t 1/2 e to the 5t, and then e to the negative 2t, negative 3 e to the negative 2t. So it's this determinant that's just these column vectors put in the columns. So this is the column for x1, this is the column for x2. And if I take that determinant, I get, the diagonal here is minus 3, e to the 5t times e to the negative 2t is e to the 3t. And then the off diagonal is minus 1/2 e to the 3t. If I combine that, I get minus 7/2 e to the 3t, which is never equal to 0. And remember, if the Wronskian is not equal to 0, then what you're looking at is linearly independent. And so we have two solutions. We found that they were solutions in the last video, and now we know that they are linearly independent, which means that they form the fundamental set of solutions. So this is very similar to the theory that we talked about for linear equations earlier in the semester. And it's actually going to help us a lot to remember these two remarks that I have here about the solutions of a system, about the ratios matching and then forming a fundamental set of solutions. You're going to see a lot of relationships with things we talked about earlier in the semester. All right, thank you for watching.